Oh, you know my person well.
Then we weed them out.
Yeah, so now signal strength is down to 2 bars. And still
Right.
not saying anything.
I can start, right?
You can start anytime.
Okay, thank you. So,
I was on it.
just remind about myself a little bit. So, my name is Pavel Korshunov, and but everybody calls me Pasha. And I'm in my 5th year of PhD study in the National University of Singapore under supervision of Wei Zhang, and he was postdoc of Larry's several years ago. Larry's postdoc in Berkeley, yeah, before. So, and today I'll be presenting my PhD research, the research I'm doing as PhD student in NUS, and I have actually 2 major projects, and one is more research oriented, and one is more like practical, smaller one, and I hope to have time to talk about both of them. I kind of found that I think it will take around 40 minutes. I hope to speed it up. I don't know. Okay, so the first project is also the title of my PhD thesis. It's a topic of my PhD thesis. So the title is Rate Accuracy Trade-off in Automated Distributed Video Surveillance Systems. So I'll start with a brief introduction and describe the video surveillance system architecture that we assume in this talk. And then I present some experiments we did with some of the video analysis algorithms, such as face detection and face tracking. And then I describe some system prototype we built, and also I'll try to formalize the experimental finding into what we call rate accuracy function, and which I will estimate for another tracking algorithm, which is block tracking. And I finish with conclusion. And so we have a lot of cameras nowadays around us, and therefore we have a lot of video surveillance systems, which all monitor the cameras. And in a typical video surveillance systems, there are a lot of human resources, a lot of human participation, that people sit and watch the screens like here, and they usually have central facility. All the streams are collected there, and people just watch the video all the time. And however, in recent advances in video analysis algorithms, and also the availability of cheap network cameras, and we have also IP network, this all allows us to build a new kind of generation of video surveillance systems, which is large scale and at the same time automated and distributed video surveillance system, where actually the part of the human job can be taken by video analysis algorithm. So instead of human, maybe the algorithms will be watching the video. And that's basically, we assume this kind of system, the large scale system, some system of scattered low cost video sensors, basically the systems where the bandwidth is a limited resource. So where the free streaming of video is challenging problem. So so the point is how to minimize the video bitrate in such systems. Research shows that actually in typical surveillance scenario, the suspicious events are actually rare. Most of the time there's nothing much going on in the system. And therefore it's not necessary to have a human guard constantly monitoring the video, but instead we can replace him with some video analysis algorithms, and they alert the guard only when something happens, when they detect some activity in the system, right? And therefore, in taking this situation into account, we want to ask the question: how much of a video bitrate we can reduce? What is the required video bitrate when we use video analysis algorithm instead of human person? Yeah. So we consider this system architecture, the architecture of video surveillance system, where we have many networked video cameras plugged in network, and there are a bunch of processing proxies distributed in network as well, and they receive the streams from the video cameras. And these proxies, they run some video analysis algorithms that monitor the video. And the video is relayed further to monitor station where the human is sitting, only if something happens, only if video analysis algorithm detects something in the stream. So most of the time the video streams here, because suspicious events are rare. So very rare something will be streamed here. Therefore, most of the time the video analysis algorithms are watching the video from cameras, and therefore we can maybe reduce the bandwidth. We can reduce the bandwidth on these links between camera and the proxy, if you find that algorithm doesn't require much of the video quality. And that's the first question we ask: how much of the video bitrate can we reduce? So we ask this question in the scope of video surveillance system, and also we first we take first operations to run some experiments to see how how much of the video bitrate we can reduce. We take face detection and face tracking algorithms. So how do we approach answering this question? So we take video or for face detection images, and we take original images and we apply different quality. We reduce the quality of this video. We keep reducing the quality. In this case, we compress it more and more, and note the point when the algorithms cannot detect the face anymore or cannot perform accurately anymore. So that's the experiments we're running. And so the algorithms we took both are from OpenCV, and first is a famous Well-Jones algorithm, and for that algorithm we change compression quality of the video and spatial quality of the video to reduce the video bitrate. We compress more or resize. And for the test we take standard MIT CMU dataset with ground truth, 107 faces. This is example picture. And for face tracking algorithms, we consider the cam shift tracking. It's a simple histogram-based tracking algorithm. And for that, we change temporal and compression qualities. And for the test, we couldn't find a standard test for the face tracking, so we have some video clips and some video of moving faces. And so the first result for face detection algorithm and compression quality is on this graph. So what is here, that on x-axis you can see changing compression quality. So this 100 to 1 is a scale of that compression software we're using. It's standard open source JG so compression software. So 100 means that the quality of the image is very good, and 1 means it's very bad. So it's the most compressed here and the least compressed there. So what we do, we take all our 507 faces in MIT CMU dataset, we compress them with particular quality, and then run the face detection algorithm on those images. And we note how many faces are detected. And we divide by total number of faces, and that gives us 1 point on this red curve. So it's a detection index, which is basically a percentage of faces detected. And you can see that while we're reducing the compression quality, we're actually reducing compression quality more and more, the accuracy, the number of faces detected stays the same until compression 11 around there. Then it starts to drop drastically. So this means actually that we actually potentially can reduce video very much. We compress a lot, and this quality 11, it actually amounts around 6% of original image sizes. So we can reduce the images to 6%, and the accuracy algorithms still remain pretty well. So it doesn't decrease much. And moreover, over here we plot the false positive index, and that means basically number of faces detected in the images, but which are not real faces, and divided by total number of faces. So that's the index, and we can see that it doesn't grow while we compress images. So it's a good result. So it's very encouraging, and therefore we wanted to test it in some more or less real environment, like some lab experiments, and therefore we shoot the video of a lab door, 5 frames per second video for like about an hour, and we got 22,000 frames. And out of that, we manually select 237 faces. We found 237 faces which happens that 138 of them are frontal. And we can see the face only if 3 consecutive frames have a face on it to eliminate some false positives. And so we pick 2 different compression qualities. So the quality 90 we take as a quality which is good for human eye. So it's a good quality of an image. And compression quality 20 is the one which is okay for video analysis algorithm. We saw in the previous graphs that it was actually 11 when it started to the sweet spot is around 11, but we conservatively take 20 just in case. And we can see that detection index so we run algorithm. So we compress all the images with compression 90 and compress all of them with compression 20 and run face detection algorithm on those images. We can see that percentage, this is basically percentage of faces detected, is almost similar for different qualities. So, yeah.
So you don't retrain the detector when you do that, do you?
No, I didn't retrain. Yeah, I just take the same detector. Yeah. Although I changed, I had another bunch of experiments which I will not present here, where I tweaked the parameters. And also by tweaking parameters, you can actually improve the quality, smoothen up the curve. So it's but the important point is that false positive also doesn't grow that much. It stays in 1%, and that's consistent with our MIT CMU results, dataset results. And another quality we looked at is with the spatial qualities. So the spatial quality it's a little bit different for the face detection because each face detection will have a particular threshold of a face size. So if for this algorithm, if face is below 20 by 20 pixels, it cannot detect it. So it's basically each face has to be above certain size. Therefore, we cannot too much reduce the video spatially, resize the video because it will lose the faces inside. So what we did then, we take each image in a MIT CMU dataset, we scale it down with B-cubic algorithm to, like, for example, 70% here, and then scale it back up to original size. And then we run the same set of experiments I showed just now, the graph. And what we can see here that while changing the compression quality, what important is that the curve, detecting curve, it stays the same. It's has the same kind of curve with relation to compression quality. What it means that when images went through this transformation, it did not affect the detection accuracy very much of the algorithm. It's very consistent with the original. The red line is original. The green line is the images which went through prescaling transformation. And we got this on expense of a higher false positive index. And actually at the same time, prescaling gives you average image size to 50%. So what does it mean? It means that if you have on the camera a very small video in a very small resolution, you transmit it to the proxy as a reduced bit rate, and then you can artificially scale it up to bigger size, and you can detect. It guarantees that this experiment shows that the detection index will be similar to as if the video would be streaming. The original size of video would be streaming from camera to proxy, not reduced one.
Why do you bother scaling it back up? Why not just operate on the lower resolution?
Yeah, because lower, it's obvious there is a threshold. So many faces will fall below the 20 by 20 pixel threshold. So of course the accuracy will be reduced, obviously. So what we want to see is that the B-cubic transformation does not affect the accuracy. So we can safely scale down and then stream and scale up. That's basically the point. And we did this lab experience also to see whether the idea can be supported by the more real experiment. So basically, shoot the video of like around 300 frames with just faces moving out near the camera and out of the camera. So basically, small faces, big faces in the video, and like a lot of motion and things like that. And original video was shot like 160 by 120 size. And the detection index there is 23%. Only 23% of total number of faces is detected. But when we each frame we scale up to like 140%, we get 57% of faces detected, because more faces go above the 20 by 20 pixel threshold. So basically in this video, in original videos, some faces are too small. When we artificially scale it up, it's become all right.
If you just made the threshold proportional to the size of the image, would it have had the same effect?
But threshold is set by algorithm. It's basically that face detection is just built in. That it cannot. It's the way it's trained. It's trained
Okay.
by 20 by 20 pixels.
I see.
It's
Okay.
it's
I thought
hard.
it was the hard-coded threshold. of the
It's a hard-coded threshold, and it's all face detection algorithms have such kind of threshold,
Mm.
because by just it's sometimes impossible by two pixels you cannot find the face anyway. So that's why they do it.
Okay.
And if you scale it to 160%, you get even higher. More faces become higher, but you get this false positive increase as well. So there is trade-off. But scaling increases accuracy, basically scaling up. So another algorithm we were looking at is face tracking, right? For this algorithm, we were considering the temporal quality, because obviously for tracking algorithms, the frame rate is more important than compression. It's not obvious, but it's important quality compared to others. So and you also can reduce if you reduce frame rate, you can reduce bit rate much faster, you can say. So the temporal quality was changing in this way. We were applying the drop pattern to the original video. We drop I out of I plus j, call that. That's drop pattern. So for each 15 frames of 30 frame per second video, we drop I frames out of I plus j. So we and I and j goes from 1 to 15. So basically, and that gives us a range of different temporal qualities. So and y I and j. So I basically indicates how many consecutive frames are dropped from the video, and j indicates how many consecutive frames remains in the video. So that's basically the measure. And to find the to find the accuracy, how the accuracy of the tracking algorithm changed after we drop some frames. What we do, we run algorithm on a original video. We note all the frames of all the centers of the faces in all the frames, and then we for each corresponding frame in a video with applied drop pattern, we also find the center of the face, and we find the distance between them. So basically, if the distance between face in original video and face in video with drop pattern is 0, then it means accuracy does not change. So that's its importance. So this drop did not affect the accuracy. If the higher the distance, the more is the error. So we measure the error basically of the tracking.
So you dropped the decoded video?
This is a motion JPEG, so we just drop simply. It's a very simplified way. So it's not MPEG, yeah.
Okay.
Not MPEG-4, yeah. So we didn't consider GOP and things like that, which is a different kind of topic anyway.
Because for MPEG, if you drop and then if you record at a lower frame rate, it's not proportional to the number.
Yeah,
of
it's
frames.
not. So the point is here to have some consistency, because in a motion JPEG it's easy to drop frames, while in MPEG you can have you drop B frames, you drop P frames, so you have much less levels of variety of quality. But the point here is to see the trend, and then to understand whether we can actually in general do it or not. So another point to note that different drop patterns can give the same frame rate. So the important difference between these two drop patterns is that drop gap. So the how many consecutive frames are dropped. That affects, which turns out it affects the frame tracking, the object tracking much more than the frame rate itself. So and here the experiments we did for the face tracking, and the graph is such that on the x-axis we plot the drop gap. So basically how many consecutive frames are dropped. And each curve is different j, is basically how many consecutive frames remain in the video. So, and plot here several examples of these curves. And on the y-axis, we plot that arrow that we measure the distance between faces in original video and with applied drop pattern. It's a normalized arrow, basically. It's around 2 pixels over here, the difference on average for all frames. So what this graph shows actually that while we increase the drop gap and so basically frame rate is reducing, right? The quality the accuracy basically of this algorithm does not change much until some specific like drop gap 8. And after that it starts to oscillate. And also for different j, which is how many consecutive frames are remaining, it does not change much on the vertical scale. You can see that the arrow does not increase that much. So what does it mean? That it means that we can drop 8 out of, so if we take the red point, we can drop 8 out of 9 frames, and the accuracy of the video accuracy of the face tracking will change just by 3 pixels. So the coordinates of the face will be different by 3 pixels compared to original video. So, and why it's oscillate? The algorithm is pretty simple. It's because it's search for the histogram into particular window, which is in the previous frame. So it knows where the face was in the previous frame. Then it comes a new frame. It starts to search in the window around that previous location. And if gap is too high, so I is too high, too many frames are dropped, the face already moved away far. So it loses the face and it goes up, the arrow goes up. But if sometimes gap is too far, so it moves away and comes back already. And it gets low as well sometimes. So it depends.
What happens if you increase the window size?
Oh yeah, you increase the window size, you get, the window sizes affects also the histogram will start to pick other things. You see, if you increase too much, it will start to lose because some other objects will come into that region, and it will the face will grow. You can say the detected region will grow. It's simple, just histogram.
So what is the window size that they use?
Window size they use. It's hard coded. I forgot. I was changing it there. So it's around. I think it's 150% of the previous. So it's around the face. So it's a blob size and increase each coordinate by 150%, I think. So it's expand by
Okay, so
1.5.
So it depends on the size of the
Oh, yeah. So they detect the face. In the next frame, it will search the previous blob plus expanded to 150%, like that.
But how does the seeding take place? Initially, at some point, the algorithm has to.
Oh, seeding is manual. First, I just set the first frame manually.
Oh, so you tell the algorithm where to look for the first.
Yeah, I don't care about.
Phase.
You see, I don't care about how algorithm good or not. I care how is it affected by temporal quality. So the first frame for when I apply drop pattern, the first frame is the same for everyone. So the initial state is the same, and then when I apply the drop pattern, there is different kind of frames will come inside the algorithm. So so I want to see the change in accuracy of this algorithm, particular algorithm, which is not really good, but I want to see how it changes if I change the video quality. Yeah. So yeah, but it's the algorithm says you set it manually.
Have you thought about making that search range dependent on your frame rate?
Yeah, I did. Not frame rate, is more dependent on the object speed actually. That's what I did, and but I will not show it here because I show another one, another algorithm which I similar kind of approach. Yeah, because that's the point. Yeah, so to make it better, make it more adaptive to the different to the change in video quality. Yeah, so I'll talk later about it. So anyway, the main point is that the drop gap is a important measure of the temporal quality for this algorithm, not frame rate. And we change compression quality for different videos. We change compression qualities and we plot the drop gap. that by this critical drop gap until which the algorithm performs well. And we see that for different compression, the drop gap does not really change that much. So the compression does not affect this histogram-based algorithm because histogram is very general. If you compress too much, the histogram doesn't change that much. So that's basically the point. And but what is affecting the drop, this kind of critical drop gap is what are the movements inside the video? How fast the faces grows, jumps around. If it jumps too much, then drop gap cannot be. Then you cannot throw away too many consecutive frames because algorithms will lose it. Well, that's obvious. So, therefore, out of this experiments, what we can take out is that for face detection algorithm, we can take compression quality 20, and we took frame rate 5 frames per second. That's just because we think that 5 FPS is enough for the face to be detected, right? And for cam shift tracking algorithm, we take conservatively compression 50, and the temporal quality 6 frames per second. This is basically based on this that for very jumpy movements, we have drop gap 4, which is we can take 4. We drop 4 out of 5 frames, which gives us 6 frames per second. And we wanted to test this experimental result on a real video surveillance system prototype, on a real network. So we use a camera, Canon camera, and also we have one PC which is proxy, which runs either face detection algorithm or tracking algorithm, and another PC has a monitor station which video gets relayed to if something is detected by the algorithm. And we built this prototype on top of OpenMesh and Endiva, which Larry should be very familiar with. And it's a basically framework for live media streaming. And how prototype work? For example, I'll show a face detection example. It has, like, you can say, 2 modes. One is observe mode, when there is nothing happening in the system, so guard don't need to be alerted. And we take compression quality 20. We don't change frame rate just to be consistent, just to check compression quality. And then, so it stays, so there's no phase, it stays in compressed mode. And when phase comes, then the compression quality changes to 90 because now human want to watch the video and it's streamed to the human station, right? And while the video is while the face is inside the video, it keeps being quality 90, and then when face moves out, the compression goes back to 20. And the result of the MJPEG video is that you can see that so this is timeline, and this is bitrate. So the bitrate when it's in observe mode stays on around 1,000 kilobits a second. When the quality jump to 90, so the face comes in the frame, quality change to 90, and it stays. It goes to this bitrate. So you can see how it's changing and this is with 30 frames per second. Yeah. We also, so that's basically the obvious advantage of the. So we can basically, when there's nothing happening in the system, it stays always in observe mode, and that means the bitrate is small. So overall, we get that if we use for face detection quality 20 and 5 frames per second, then gets us 29 times reduction in bitrate for MJPEG. And for face tracking, if quality 50 and 6 frames per second, it's 16 times reduction of the video bitrate in MJPEG. So, these findings give us so you can see that we have a dependency between the quality of the video and the accuracy of the algorithm, which we call quality of the video is the same as video bitrate. So the worse the quality, the smaller is bitrate, right? So and that gives us a notion of rate accuracy function, which is somewhat analogous to the rate distortion function, but for the human eye. Rate accuracy is for algorithm. So how to find? So what we want actually to have is we want to have a desired accuracy for the algorithm, and like detection index or face distance ratio, and we want to find such video quality, like like compression and temporal spatial, and we want to find such videos that minimize the video bitrate, and it's all in subject to environment conditions because the lighting changes all these effects. So this is ideal rate accuracy function, very general view on it. But how to find in a real situation? So one way is to run experiments. You have you change video quality and therefore video bitrate. You observe the change in accuracy in the video analysis algorithm, some video analysis, any, right? And this means that you can have a different way to change the video quality. There are many ways to change it. You can drop frames, you can reduce compression. There are different compression methods, different way to reduce the quality. So we call it video adaptations. And there are many video analysis algorithms. So it brings us to many experiments, too many experiments. And can we use some analysis instead? Maybe we can have some approach which we can estimate of this trade-off of rate and accuracy. So propose the notion of video features, which we call it. As video features is like property of the video with respect to analysis algorithm, and video adaptation. So we have divided three categories. First is something related to that object of interest which algorithm is looking for. So such like size of the object, speed of the object, color of the object, which is affecting the accuracy of the algorithm. At the same time, this property is affected by video adaptation. The speed affected by dropping frames, size affected by the spatial resize. So this kind of property. Another category of property is something internal for the video analysis algorithm, something the algorithm is looking for in a video. Because so either it's histogram that algorithm is focusing on. So histogram can be affected by video adaptation. At the same time, that histogram is some property of the video general, which algorithm is using to find the object or track the object, or pixel intensity, or hard features for the face detection algorithm. And another category is basically if algorithm is learning, it's trained algorithm. There is always some probabilistic error of detecting or not detecting, or tracking or not tracking something. So this kind of it's still a property of a video, but it's very hard to understand where it's come from. It's basically it's a error of the training stage, you can say. But still depends on what the pixels values are. So the analogy is basically, I give a small analogy with basketball. Like basketball bounciness, it depends on what is the air pressure, what is the stretchiness of the leather, and the optimal combination of this many parameters gives you the desired bounciness, right? And you don't want it to jump too high, you don't want it to jump too low. So the same is video features. It's like some properties of the video, which and in the same time you have here we want to reduce video bitrate, and here we want to reduce the cost of the ball, right? So you want to find the optimal parameters for the minimal cost. So here you want to find the optimal combination of video features for the minimal bitrate. So we did that. So here we did the analysis of based on using this video features notion. We did analysis of the blob tracking algorithm. The blob tracking algorithm is another quite recently introduced OpenCV algorithm, which is Kalman tracking based on frame differencing blob detection. So, and the video feature we focus on is the speed of the object. So speed of the object, the simple video features is affects the accuracy algorithm, and video adaptation, we drop frames. So the more you drop frames, the faster the objects start to move. So the more the tracking is affected. And we use a video from PET 2001. So it's a simple video. The car just moves linearly increasing linear speed, linearly increasing width because it's moving towards the camera. And you can see this is when you have two frames differencing, this is what it gives you the blob. So here the two of these frames which were different, the difference taken is between two frames which are far away apart. So you can see that blob becomes long and big. and that makes it it gives you yarrow in the tracking of this object. So did simple analysis. So in this picture you can see this is the original car. This is a car. This is a frame differencing when frames are very near to each other. There's no dropping the original video, and this frames when we drop like around 10 frames, and that's become the blob detected is very big. So to find out the yarrow is basically what it is if we model the car moving as a this simple picture. So in original video, what is actually detected blob is a union of the car in current frame and the car in the previous frame. So it's a union of these two these two cars. So it gets the yarrow, but it's small because the frame rate is fast. The frame rate is big, so this yarrow is small. So when we drop the frame, the frame differencing gives us this blob because it will be the union of this car and with this car in the frame before that. So it introduced the yarrow to us. So to find the yarrow, yarrow is basically the distance between these two blobs. It's the same frame but with different drop pattern. And if use some analysis, we can find that the distances can be described as such function, which delta x0 is the change in the change in original distance car moved, and the delta w is how big the width grown compared to the previous frame, because car is moving towards the camera, so it's actually getting bigger as well. And so we also compare. We don't compare with the ideal case when there is no yarrow. We compare frames with dropped pattern with frames without drop pattern. So it's 30 frames per second compared to something with applied drop pattern. And if we extrapolate this, so if we using this distance for all frames, we can describe the yarrow estimation as this function. So basically for all video where we drop I frames out of j, I plus j frames, the same drop pattern we apply, we drop I frames out of I plus j. So I is how many drop consecutive frames we drop, and j is how many remains. And it can be described as this function where it's proportional to the yarrow is proportional to how many frames you drop in the video consecutively, and it's inversely proportional how many consecutive frames remains. And C1 and C2 are constant, which it's not really a constant. It's basically the parameters which depends on speed of object and how fast and how the width of object is growing. The original video. So, and if we plot, so we did the same experiences for phase tracking, where we plot drop gap on the x-axis and the yarrow on the y-axis. And what you can see here that when we increase the drop gap, the yarrow grows because the frame differencing become bigger, the blob grows, right? So when you differentiate frames which are far apart, the resultant blob will be bigger than if you differentiate the frames which are nearer to apart. So it grows linearly. And for different j, so for different number of frames which are consecutively remaining, the angle of growing is different. So you can see that it's proportional to the I. It's linearly growing when I is increasing, and it's inversely proportional to the j, because you see if j is 1, then the angle is around 32 of the curve to the x-axis, and when j is 3, the angle is around 11. So it's exactly 3 times smaller. The angle is 3 times smaller than the angle for the j1, which is exactly what this formula is describing. So for j equal to 1, it will be I c1 plus c2, and for j equal to 3, it will be 3 times. The yarrow will be 3 times smaller, and that's exactly what it is. So and that means that the estimation we can do estimation of this experimental finding pretty well for some cases, yeah. And so it's a simple speed of object, and it's just simple frame dropping operation. It's not some compression, which is difficult to analyze. But this gave us also idea that we can also improve the algorithm. We can modify this tracking algorithm to compensate for this dropping of the frames and this, because we know how many frames we drop, and we can use the previous knowledge of what was the speed of object in the previous several frames. We track the history of the speed of object, and then when we know that next 5 frames will be dropped, we can estimate where will be the object. And knowing this information, so we use the adaptive Kalman filter to compensate for that jump in speed and jump in width. And when we do that, we run this algorithm again, and we can see that the angles go down. So what we want, we reduce, we flatten the curves, and that means that the arrow doesn't grow as fast. It doesn't. We eliminate that J component, so it's no more inversely proportional to J. And now the arrow doesn't grow fast when we increase the drop gap. That means we can reduce more of bit rate, and the accuracy will stay still the same. So that's basically when we are aware of the of what kind of video adaptation we use, like dropping frames or something else. We can modify algorithm to compensate for it, to be adaptive to it. For why the red line still grows high, because when J is 1, that means only 1 frame consecutively remains. So 1 frame, then 5 frames drop. 1 frame, 5 frames drop. So we don't know the actual original, the speed of object, and its growth, the real growth inside of the object, because of the size of the object, because we have no real history. We only have big gaps between 1 frame, big gaps. So it doesn't, the algorithm doesn't compensate for the drop.
If you want to do surveillance, in principle, what you would like to do, I guess, is to have some guarantees that you're not missing critical events, particularly if they depend on the speed of objects. Or let's say there is a known range in which of speed that an object can have, like a car in a certain environment.
Yeah, that's
so it
true.
becomes interesting to know how far the camera is away from the spot that you're observing, because that's a factor on the speed with which.
Yeah, we didn't take in account the calibration parameters, because that's also, of course, important, because you need to know. But you see, this one, it's adaptive in the sense that it's adaptive to it, based on the video itself. So it takes several consecutive frames. If it's 30 frames per second, several frames, like 4 frames per consecutively, record the adaptive Kalman filter learns the speed of the object. And when you know that I'm going to, after 5 frames, I'm going to drop 5 frames, then the Kalman filter just this information is inside this Kalman filter that next 5 frames are dropped. Then it will be estimated the speed will increase by such. You can estimate the speed, how much it will jump. With certain arrow, of course, because if it's moving towards you, it jumps faster than. So it's it's not really that simple, yeah. Especially if it's not linear movement, because if it's going in circle, then it's actually the width may start decreasing instead, and that's all. It's all. This is very simplified view on it. It's just to raise a point, basically. So, and then the point is that video bitrate can be reduced significantly for certain video analysis algorithms, and hopefully for many. And we also can use analysis to estimate this trade-off between rate and accuracy of the algorithm. If we know some information about algorithm, we know something about the video, and which we call video features. And when we know something extra, we can analytically reduce the number of experiments we have to run. And we also can design video analysis algorithms which are adaptive towards the change in video quality. So this is very important. Oh. And I was there to say, okay, it's already late. I have a very short demo. Oh, so long. I'm sorry. So I'll show fast. So that was the research project. This is a small tool for, it's basically scripting language and a small tool for the working with media streams. So the motivation was that it's not many tools are available for live video manipulation, live stream media manipulation. Like Encast actually box targets the same problem. So how to arrange videos, several videos on one screen, how to have some event-driven change of layout or react to some network changes and semantic the content changes, and easy to use. So we create the Plasma is a scripting language which is an extension of Tcl, and we focus on the special adaptations and special composition of the streams. And what streams are treated like, they're treated like widgets. It's basically arranging the streams is similar to arranging the widgets on the screen, like buttons and forms and all that. So also have a network and also have events in the language supports events, which can be also networked or content based. So if loss rate is too high, then we do something about the stream. And it's based on uses FMPEG, LAME, OpenMesh, and Endiva. So the simple example is like you can define the object like container, or you can define the object with source from some video camera in an RTP stream or HTTP stream, or some file in local file system. And then you define this object, and this means that left object is inside this container, and then you arrange them using mpeg command, similar to TK widgets basically, and you arrange them. Oh, it's big. It's container. Oh, so container left, container right, container play. I'm sorry, misspell the mistake. And you arrange them using some side switch. You arrange them on one side by side, for example. Or events is something like similar to TK events. You define events, for example, have motion, and for object which is passed to this event, it will check whether it has motion. And we create the object camera with a camera from Axis Camera, with a stream from Axis Camera, and then you bind this event to this camera object. And what will happen is that Plasma will, every frame of the video, it will check whether the object has motion, whether the camera has motion. And if it has motion, it's check if another object exists, and if it doesn't exist, it creates the object from this with the same source and records it into some archive file. So you can create another event which say doesn't have motion, and then it stops recording. So this kind of events you can have in the system. So, and I have a very short demo. Basically, this is a script. What I say, it's basically arranging two streams, two live streams in side by side, and it's just like 5 lines. And okay. Yeah. So what I do, I just copy line by line into the interpreter, the script interpreter, and then it's based on mesh. So as I said, and you create the container. We create the source 1, source 2. Then we pack together side by side. Then we say play. It will start playing the video. So it's received 2 streams from 2 Axis cameras, and you can see that. So basically, it arranges 2 side by side. So 5 lines, it arranges 2 video streams side by side. So this is one demo, and flickering is a bug in the system, obviously. So another one is with events. So for example, the situation is such that maybe guard watching the video, the surveillance guard watching the movie, and in the small corner, picture to picture, there is a video camera, and when something happens in the video camera, when motion is detected in the video camera, it rearranges the screen. So it's he watching the movie, then the motion there happens, detects the motion, then it will rearrange the screen that now the camera is big and the video is small. So this kind of example. Yeah. So this is that the script is several lines. So it shows the events how they're done. Okay, that's all.
During the Super Bowl.
Yeah, exactly.
That's it. I'm so late. Whew. okay, you can ask questions.
Did you buy that outfit just for today?
No, I bought it for the 2 years ago conference.
Is this the first time you've worn it since 2 years ago?
No, I also post the presentation. I also wore it. Every year I do it, wear it once around there for conference.
Anybody heard the story about, what was the guy that did Linux, Thompson? Ken Thompson in the suit. Turns out that at one point Unix got big in AT&T, and they decided they wanted him to go before the board of directors to give a presentation about Unix. Now, Ken Thompson has one outfit. He wears jeans and a t-shirt and nothing else. Well, actually puts on a jacket because they're back east when it's cold. So the management said, no, you've got to get a suit. You've got to get dressed up. I mean, you can't go talk to the board of directors looking like that. So he goes and buys a suit, goes to the board of directors, does a presentation. The presentation was great. Everybody loves it. Comes back in the next week and submits his reimbursement form that says, would you buy that suit? I wasn't going to. And I think in the end they did pay for the suit.
Okay, no questions.
Great.
Okay, I have one
Oh,
question.
you have, okay.
So, in the beginning part, you did two things that downgraded the quality. One was just pick a lower JPEG
Yeah,
compression
compression,
number,
yeah.
and the other was scaling down and scaling back up.
Yeah.
So those seem like they're both doing the same sort of thing of throwing away high frequency information. Was the point comparing which of those is better to do, or I didn't?
They're a little different because compression does not change the size of the face. Actually, it's just throwing the frequency. That's exactly what compression does. But scaling, it's actually reduce the resolution of the video, of the image. So it's
But then I thought you scaled back up. So after you would do that, you
oh
in
yeah.
both cases
Then after
you'd
you
have
do
the
that,
same-
Bcubic doesn't really throw away the frequencies exactly. Not only that, it has some. It's not exact. It's averaging of the four neighbors. Actually, the Bcubic, it's when you scale up, it's averaging it's what it does. It expands each pixel. Yeah, so it's not exactly the compression. It's a bit different transformation. So it's a different transformation which affects the bitrate, obviously, but it's not exactly the same transformation. It's not. It doesn't have a Fourier transform over there. But that's the point. That different transformation differently affect the video, and it's very difficult to say in advance how it will affect the accuracy of the algorithm. That's why we have to do experiments. And then later, I'm fed up with doing so much experiments, and I want to have some thinking which takes just 1-2 weeks, and then and you get already some understanding and results, right?
So in one of your results, you show adjusting of the video quality depends on this activity going on or not. So there's a curve like that, right?
Oh yeah.
Yeah, and then so I was wondering if you actually use a MPEG, you will kind of do that already by the algorithm, by the MPEG algorithm.
Yeah. So of course,
Because
like
if there's activity, then
yeah,
the period will jump.
we have.
There will be more iframe than
I agree.
difference.
Yeah, I agree. Then there is also H261 or H263. Those which are depends on the motion, so they encode only those blocks which are changed.
Right.
But that's not the point, because here the point is that because activity is a face detection. But if just a cat walks up, the face will not be detected, but the algorithm will adapt to it, right? So we don't want to. It's not about the codec. It's about the how we can based on the algorithms how we can manipulate the video. So basically that what you say the MPEG algorithm, you can reduce it even more if you know that there is nothing important in the video. You can even you can compress it even more. You can compress with a lower bitrate because there's nothing, and it will reduce even more anyway.
So one way I'm thinking is if you have some sort of tracking or detection algorithm embedded, and then you can use regional interest related kind of codec like MPEG-4 and stuff like that.
Yeah.
So that would be a way to combine both the activity and also the motion.
Yeah. That's true. another thing also, you see, this one we change only the compression, but then the frame rate is another story. It doesn't change the frame rate automatically. If it doesn't, nothing happens, it still will be 30 frames per second. But because we know that face detection, so face tracking doesn't need high frame rate, we reduce the frame rate. But for the once face start to get tracked, the reframing increase. So it's a more general picture than just while in the same time, what the experience shows that you can or you should design the encoding algorithms which are targeting this kind of situations, which are aware of video analysis algorithm, and it's more because normally encoding algorithms are for humans. So the better quality, the higher quality is the better. But for video analysis algorithms, the important thing is they don't need such high quality. So you can create encoding algorithms which targets video analysis algorithms which are more deterministic in nature, like if they're aware of what algorithms are looking for, not distortion, but actually different things. So reducing distortion is for human. That's the point of every encoding algorithm. But for video analysis algorithms, it's not necessary just to target the reducing distortion. There are something other things. Yeah, basically. But you're right. I was thinking about the region stuff, but I have to get somewhere algorithm encoder. That's all. Okay.